So this is another table problem, and this is page 4, and it's problem 2016, problem number 1 from year 2016. I decided to skip over page 3 because it had some things that we hadn't covered this year. So just go ahead and go to this next one. It says water is pumped into a tank. Okay. All right, so I'm not going to do this one for you. I'm going to give you some hints along the way, and then hopefully you're able to complete it. You always can check your answers or see if you're on the right track by looking at the answer key that's attached to my website. Okay? All right, so looks like water is pumped into a tank at a rate modeled by this thing right there. And the first thing that I always like to do when I find a function like this is to recognize it is a rate that we're given. Okay, it's not the amount of water, it's the rate of water, and this is water that's going in. Because I'll always forget, W of t, is that water going in or out? I just am not very smart sometimes. All right, and it's in liters per hour from 0 to 8. And the other thing I noticed is this looks like we have another function up here, and it's from 0 to 8. So we're setting up the same intervals there. Where t is measured in hours, water is removed from the tank at a rate modeled by that guy, and this is also a rate, and this is water coming, and it said out, right? Water is removed. So I just like to label those things. So here we have a chart, and the chart is water coming out, but we only know certain points, and this is the rate at which water is coming out. It's not 1,340 gallons, it's 1,340 gallons per hour, right? At that moment. And this is water going in. And it is differentiable, of course, so they're setting up that we could possibly use the mean value theorem or intermediate value theorem, and decreasing, and also integrate or differentiate. And decreasing, so this is always decreasing, it's always going down. Selected values of R of t, and R of t is that guy, water coming out, are shown in the table above at time 0, and there are already 50,000 liters of water in the tank to begin with at time 0. So we're already started. As soon as we walk in, we notice there was 50,000 liters of water in the tank. All right, let's try the first one. Estimate R prime of 2. Show your work that leads to your answer. So this is water coming out. That means it's this guy right here. And R prime of 2 would be in that location, which is actually really easy, right? All they want you to do is set up slope. Okay. And part B. Indicate your units of measure, so you are going to have to say it's going to be liters per hour squared, right? Because we're going to be then at acceleration since we found the slope, or the rate of this rate. Okay. Next part. Use a Riemann sum with 4 subintervals indicated in the table to estimate the total amount of water removed from the tank during the first 8 hours. Is this an overestimate, an underestimate of the total amount of water removed? Give a reason. Okay, so I definitely would go ahead and make a little graph of our points. It doesn't have to be real nice, but we have 0, we have 1, we have 3. Looks like they're different widths, right? And then we have 8. And I would label those, put the points. Technically, you could do it without. Remember, we're doing a left Riemann sum, so this would be the base, and that would be the height. And then this would be the base, the difference, and that would be the height. But I think it's nice, especially since they wanted underestimate or overestimate, to put a little picture. But yeah, you basically just need to build rectangles, right? Up to the heights, wherever they are, and find the area of those. I think it said 4, yeah. 1, 2, 3, 4. 4 rectangles. It did also ask if it's an underestimate or overestimate, so just look at the rectangles, whether they're bigger or smaller. But you definitely need to talk about, to justify that, talk about whether the graph is actually increasing or decreasing, right? And maybe even the concavity. When it's increasing or decreasing, talk about concave up or down. So you do have to use some of those terms to be more specific than just the rectangles are bigger than the graph or the rectangles are smaller than the graph. That might not be quite as specific or using the vocabulary they might want. All right, part C. Use your answer from part B, so we have to use this answer, to find an estimate for the total amount of water that is in the tank to the nearest liter. So this was just water coming out of the tank. Remember, we started with 50 $50,000. And I typically always highlight that because you know you're going to use it eventually. Maybe not on the first part, not on the second part, but on part C, you know you're going to use that number. We're starting with the 50,000, and we have water that's going into the tank, and we also have water that's coming out of the tank. From part B, you should have found this number already, and for part C, you're now going to know water going into the tank, so you need to integrate this. This is the rate at which water is, so we're going from 0 to 8 hours. Remember, this is calculator required, so you would have to write that down, but you wouldn't have to integrate by by hand. And don't integrate by hand because you don't have enough time to. You have to use a calculator to be quick. Does that make sense? So we have 50,000, we have water coming in, we have water coming out, and that should be your answer. So you need to go ahead and set it up and then get those three values, find out what your answer is, use a calculator. All right, and last part. Last part is D. For t values from 0 to 8, is there a time t when the rate at which water is pumped into the tank is the same as the rate at which water is removed from the tank? Explain why or why not. So the interesting thing about this, if you're specifically looking at the wording of it, it's not asking you for the time. It's saying, is there a time t? Right? A time t that's guaranteed to happen, which makes me think intermediate value theorem or the mean value theorem. Okay? So which one are we going to use? Well, we need to look and see what we have. They're asking about the amount of water, right? So I know that we already have a chart up here that kind of does whatever it's going to do. It starts up higher, and then it looks like it's going down and down and down. So I would use a diagram to help me on this, and I would go ahead and make sure they're labeled and everything like that. But I would talk about this graph. This is R of t. R of t is somehow going down, right? And then I would also get a graph of the other guy, which is W of t. And W of t is water going in. So what would that graph look like? I'm not sure. You would graph it on a graphing calculator. The units are going to be hard because they're large number of units. But if they don't cross, then it wouldn't be guaranteed. And if somehow W of t does something like this, well, if this point is above and that one's below, if this one's above, that one's below, then they're guaranteed because they're both continuous or differentiable, right? I think that would be technically quoting the intermediate value theorem, right? The IVT. I don't know why I put an M there, but I would call it intermediate value theorem. And you need to do a good job of showing it because a picture is worth 1,000 words, and then also explaining in words. Anytime they ask you to explain, you need to do it with words, okay? So good luck. Make sure to check your answers afterwards, and be nice to yourself. If you get beat up by this one a little bit, that's okay. We'll keep on working and come back strong.